Hello guys, Tebang Paddy here. Welcome to our PIC assembly language programming videos. On this video, we'll be doing interrupts. We'll look at what are interrupts, how do they work, and sources of interrupts. Now, for this video, we'll be using the PIC 16F818 for examples. Right. Now, let's get started. What are interrupts? From the term itself, interrupt, the meaning still holds for the PIC applications. Now, for instance, let's say you are a student studying for exams. You have upcoming exams and you are preparing for examinations. Now, you are studying in your study room. While you are busy studying, someone comes and knocks at the door. So basically, they disturb you. They interrupt you from studying. Right? And now you leave the studying process to attend to whoever is knocking, assuming that they are asking you to assist them of something. You do so, and then you come back to continue studying. Now, when you come back, you continue where you left. Right? You don't start afresh. You continue where you left and continue studying. Now, if ever it happens that they knock again and disturb you again or interrupt you again, you will attend to that interrupt, do or assist them with whatever they are asking you to assist them with, and then you come back, you continue studying where you left. Now, that meaning, that principle still holds for the PIC interrupts, right? So in the PIC microcontroller, how are they used? How are interrupts used? Now, you will have the main function, the microcontroller executing the program that falls under the main function, doing its main function. When it gets an interrupt, it leaves whatever it's doing in the main function, goes to what we call the interrupt service routine, executes the program that is under the interrupt service routine. I mean, it's performing the function it's supposed to perform when it gets an interrupt, and then when it returns from the interrupt, it goes back to the main function, continues where it left just before it was interrupted. Right? Should it be interrupted again while in the main function, it will leave the main function, go into the interrupt service routine, perform the function it's supposed to do for the interrupt service routine, and then comes back to the main program, continue where it left. It will forever do so. So that's basically how interrupts are used in the PIC microcontroller. How do they work? How do we implement interrupts in our program? Now, what is on the left hand side is what should be familiar to you by now. This is the normal program which we have been doing, where you have power on or reset, and then the PIC will always start executing instruction from address 00 after any reset. So that being our reset vector, right? And then you initialize, and then after initializing, you perform the main function, what was asked of you to do, right? Now, in this case, to enable interrupts or to make use of interrupts, this still stands, but when you initialize, you also enable the interrupt which you want to use in your application. You are going to enable it at this initialized stage, right? Now, it will be reset vector, go to initialize, you set up your IO pins and other things, and then you enable your interrupts, and then you come into your main function. Now, when an interrupt takes place and you did enable that interrupt, it's going to jump to what we call the interrupt service routine, which starts at address 04 there. So that address 04 is known to be our interrupt vector. Now, this interrupt vector, it is always 04 for the PIC 16 microcontrollers. For the PIC 12 and then the PIC 16 microcontrollers, the interrupt vector is 04. For other versions of microcontrollers, that interrupt vector may be something else. For the PIC 18, for sure, it's 08. And then for PIC 18, there's higher priority interrupts and lower priority interrupts. In this case, we just have only one interrupt vector, which is 04. So whenever you get an interrupt, it jumps to address 04. Right? And now When it gets to address 04, it performs whatever that is supposed to happen in the interrupt service routine, and then it clears the interrupt flag before it returns from the interrupt. It has to clear the interrupt flag. Now, the interrupt flag is an indication that the interrupt took place. Right. Now, this interrupt flag is set automatically and takes your microcontroller to the interrupt service routine. You need to service the interrupt, clear the flag before you return. Right. Now, we need to clear the interrupt flag before we return, because this interrupt flag, it is set automatically when the interrupt takes place. We clear it and then we return from the interrupt, and then the CPU will go to the main function, continue from where it left just before the interrupt, performing the main function. Should it get another interrupt, goes back to the interrupt service routine, address 04, starts executing the interrupt function, clear the interrupt flag, return, and continue where you left in the main function. That's basically how the interrupt works. Now, for the CPU or for a PIC to jump to the interrupt service routine, the interrupt flag is automatically set. And when that interrupt is enabled, that enables the CPU to jump from the main function to the interrupt flag, to the interrupt service routine. Now, if it happens that you return without clearing that flag, without clearing that you have serviced that interrupt, you return, that flag is still set. Immediately after you return, you are going back to the interrupt service routine, meaning you won't get a chance to continue with your main function. It's going to automatically take you back to the interrupt service routine, because that interrupt flag, it is still set, indicating that the interrupt happened or the interrupt was not serviced. So you need to clear, after servicing the interrupt, you need to clear the flag so that when you return, you wait for another interrupt. You are not automatically taken back because you didn't clear the flag. It's very important that you clear the interrupt flag, right? So that's basically how we make use of interrupts in our PIC microcontroller. What are the sources of interrupts? For the PIC 16F818, we have 9 interrupt sources. There are 9 sources which can cause interrupt in our PIC 16F818. But it doesn't mean we're using all 9 of them. You can enable only the ones you are interested in. These 9 interrupt sources can be enabled individually. So you will enable the one you are interested in, right? So the 9 interrupt sources are the timer 0 interrupt. The other one is the RB0 interrupt. The other one is port B on change interrupt. Another one is EEPROM write complete interrupt. Then the other one is ADC complete interrupt. The other one is the synchronous serial port interrupt. Now, this serial port is the one which you can use for implementing communication systems or communication protocols like the I2C or SPI. And then we have what we call the capture compare interrupt, the timer 1 interrupt, and then the timer 2 interrupt. Those are in total 9 interrupt sources. But for this tutorial, we are going to use the RB0 interrupt. Now, RB0 interrupt is controlled by those 2 bits there. These bits we'll discuss and find out where these bits are found. These bits can be 0 or 1. So this one is the interrupt enable. The int E is the interrupt enable bit. Now, that bit has to be set for that interrupt to be enabled. So each and every interrupt has the E bit, the enable bit. So on default, all of these interrupts are disabled. So we can enable just this interrupt, and in our application, use only this interrupt. Right? If you want to use 2 interrupts, you can enable both of them and use them in your program. Right? For this application, we're just going to use one interrupt, being the RB0 interrupt. Now, the RB0 interrupt says you can get an interrupt if pin RB0, port B0, is used as an input and its logic changes from 0 to high. That is what we call the rising edge. We can generate, or we can get an interrupt when the input on RB0 changes from 0 to high, for the rising edge, or when that input changes from high to low for the falling edge. So we need to enable this interrupt and then set whether we want the interrupt on the rising edge or we want the interrupt on the falling edge. So this is the enable. To ensure that this interrupt works, we need to ensure that this is enabled, right? This is the flag. This is the indicator that the interrupt took place or not. Initially, we make it 0 when we enable the interrupt. So this one is 1, that one is 0. So, and then that's an OR gate, right? And then for the CPU to be interrupted, you must have a 1, meaning when we enabled this interrupt, this bit will leave it as 1. That interrupt flag will automatically be set when the interrupt takes place. So when this bit is set, the output of AND gate becomes 1, because this one we are going to initialize it with a 1. So the output of that AND gate is going to be 1. Anything OR with 1 becomes 1. But for the CPU to be interrupted, there's what we call the global interrupt enable, right? No interrupt will take place if the global interrupt is not enabled. So this is the main control. So this must be 1 for any of these interrupts to work, right? This must be 1. So we're going to make global interrupt enable 1, and then we're going to make RB0 interrupt enable also, we're going to make it 1, right? That will set up our interrupts. Now, when the state of the RB0 changes from 0 to 1, if we are using the rising edge, this bit will be automatically set to indicate that the rising edge was detected, right? And then once the rising edge was detected, this generates an interrupt. The output of that AND gate is odd, there becomes 1. You end it with GIE. It takes the CPU to address 04, the interrupt vector. Now, at the interrupt vector 04, you execute the ISR function, and then you have to clear the flag. In this case, the flag we're going to clear, it is that int f, so that the output of this AND gate becomes 0, and now the actual instruction to go to 04 also becomes 0. We are going to clear this flag before we return from interrupt, so that when we return from interrupt, when this is 0, the output of that AND gate is 0. You OR 0, assuming that all of these are going to be zeros because we disabled them. ORing with a 0 there, you get a 0. But even if we enabled the global, that 0 there makes sure that we don't go to interrupt. When will we go to interrupt again? If that flag becomes set. If another interrupt takes place, that flag will automatically be set. You don't manually set that flag in the program. It will automatically be set when the interrupt takes place, or when that RB0 changes again, that bit will be set, and then this will make this AND gate to have 1, you OR, and then the AND gate gives us go to address 04 again. Perform the interrupt flag, interrupt saves the routine, clear the flag before you return. So the same principle can be applied to the port beyond change interrupt. It can be applied to the timer 0 interrupt. It can also be applied to other interrupts here, because they are all abiding by the same rule. There's interrupt enable, and then there's interrupt flag. The interrupt flag is set automatically when the interrupt takes place, and you always have to clear the flag before you return from the interrupt, so that you wait for the next interrupt. You don't keep on going back to the interrupt due to one interrupt which took place. You save this, but you didn't clear the flag. You need to clear the flag so that whenever you go to the interrupt, it's a new course of interrupt. It's not the old course of interrupt, right? But now the rest of these other logic, they are the same to what I just described in terms of the RB0 interrupt, right? So for this tutorial, we are just going to use the RB0 interrupt. Let's look at int E, int F, and then the GIE. Those are the 3 bits we're interested in. Now, looking at the intcon register. The intcon register of your... Let's go and look at memory organization. And now when we look at memory organization, there are registers there. Incon register found in all the banks. Found in bank 0, bank 1 up to bank 3, right? Incon register is also one of our special function register. But now the incon register is used to enable and monitor interrupts. To enable and monitor interrupts. So let's look at that incon register. Let's look at that incon register. It has 8 bits like all registers in your PIC microcontroller, 8-bit microcontroller. Now, bit 7 of that incon register is that GIE we spoke about. This GIE bit, which is supposed to be 1 for any interrupt to work, that GIE must be 1. And then it says here, enables all unmasked interrupts. But if it is 1, if that bit is 0, all interrupts are disabled. No interrupt will take place. So we need to enable that bit 7. Right. Bit 6 is the peripheral interrupt enable. Peripheral interrupt enable, it means we are now enabling. These are called peripheral interrupts. If we want to make use of any interrupts falling under the peripheral interrupts, first we must enable this one. And then we can individually select which one do we also want to enable. So we'll enable the peripheral and then select this one if we want to enable the EEPROM, and then the rest we leave them disabled, right? But for any of these ones are called peripheral interrupts. For them to work, the peripheral interrupt enable must be set. But for our case, or for this tutorial, we are not going to use any of the interrupts here. So the peripheral interrupt enable, we are going to make it 0. But the global, we need it for any interrupt, even the peripheral ones to take place. You see, for the peripheral ones, this is where it is. For any of the interrupts in it to take place, this must be 1, because if ever you get an interrupt from any of the sources there, that's a 1. If you end it with a 1, it can go through. But if that is a 0, any interrupt from this side will always result as a 0 on the other side. Right, now, we are not using peripheral interrupts, so we are making that 0, but we are using the RB0 interrupt, and then we need GIE to be 1 for any interrupt to work. So GIE is 1. This one, PIE is 0. And now we are not using timer 0. This is timer 0 interrupt enable. We don't want to enable timer 0, so this bit 5 becomes 0. Bit 4, it's RB0 interrupt enable bit. We want to enable this RB0 interrupt. So this bit will be 1 if you want to enable the interrupt. So we want to make 1. So we have 1, 0, 0, 1. Right. So that gives us 9 in hexadecimal. The upper 4 bits give us 9. Let's look at the lower 4 bits. Lower 4 bits, port beyond change interrupt. We are not using port beyond change interrupt. Let's disable it. Now this one is timer 0 interrupt flag. We are not using timer 0 interrupt, and then this is just a flag. It's not an enable bit, but now in any case we initialize it as 0. All the flags, remember, it's an indication that the interrupt took place. Initially we start with a clean slate. No interrupt has taken place here. We clear all the flags. So timer 0 flag will be cleared. The RB0 interrupt flag will be cleared, because at this stage we are initializing. No interrupt has taken place. Port beyond change interrupt flag, we make it 0. So the value becomes 9 in hexadecimal and then 0. That value is the value that we have to put into the incon register to enable our global interrupt and then the RB0 interrupt. Right. And then that's actually what we will do on incon, moving 90 into the incon register. Now PIE has to do with if we want to enable those peripheral interrupts, these ones. We are not going to touch the PIE because we don't want to enable any interrupt there. But what I've done with the incon will still apply to the PIE if you want to enable a specific interrupt in the PIE register. Now, these are the interrupt flags for the PIE interrupt. So you can see for the PIE, peripheral interrupts, these are the enable bits. These are only enable bits. Now, the flags are on the PIR. Peripheral interrupt flags, they are here. So let's say, for example, if you want to enable timer 0, you're going to the PIE, bit 0 enables the timer 0 interrupt. But on the PIR, bit 0 is the flag, is an indicator that that interrupt took place or not. So the PIR is the flag, the PIE are the enables for those interrupts. On the incon, we have timer 0 interrupt which we can enable. We have RB0 interrupt which we can enable, and we have port B on change interrupt which we can enable. And on the very same incon, the flag for timer 0 is there, the flag for RB0 is here, and the flag for port B on change is also on the incon register. So we don't have two different registers for the enable bits and for the flag bits, right? Whereas for the peripheral, we have two registers. The one for the enable bits, enabling the interrupts, and then another register for indicating if that interrupt took place or not, right? I'm not going to discuss the PIE and the PIR registers because I'm not using the peripheral interrupts. I'm just using the RB0 interrupt, which is found on the incon register. Both the enable bit of the RB0 interrupt and the flag of that RB0 interrupt, they are both on incon register. I just need to set up the incon register, right? I do nothing on the PIE, nothing on the PIR. Now, option register. Not all of these 8 bits of option registers are useful for interrupt. But looking at bit 6 of this option register, this is where we select the edge where the interrupt is going to take place. Whether we choose the rising edge, interrupt is on the rising edge of RB0, or interrupt is on the falling edge of RB0, right? This is where we select the edge which should cause the interrupt, either a rising edge or a falling edge. You will clear or set this bit. You will say bit set file, option register, bit 6 to set the rising edge, or you'll say bit clear file, option register, bit 6 to select the falling edge and interrupt on the falling edge, right? So the significance of the option register in terms of interrupts, RB0 interrupt, we look specifically at bit 6. The rest of those bits, they have nothing to do with interrupts, right? And now, let's look at how we can use interrupts in a form of an example. Let's look at how we can use interrupts. And in this case, we're going to focus on the RB0 interrupt. I said for us to focus or to implement interrupts, we're going to have two flowcharts. The one for the main program, and now the one for the interrupt service routine, where the CPU jumps from the main program, starts executing what we call the interrupt service routine from the interrupt vector address 04 all the way to what instruction says we should do, up until we return from interrupt and goes back to the main function. Let's implement this practically now. Now the example that we have says, draw the flowchart and write an assembly program to do the following. Implement a 2-input exclusive OR gate using RA0 and RA1 as inputs and on port A, and use RB2 as an output for this exclusive OR gate. Use RA0 and RA1 as inputs and use RB2 as the logic output, implementing a 2-input exclusive OR gate. That's what we want to do, right? So we are going to create our flowchart, set up our inputs and outputs, and start implementing an exclusive OR gate there, right? But now the question further says, when RB0 interrupt occurs, rising edge, meaning it says here we are going to use the rising edge. We need to set up the rising edge. When RB0 interrupt occurs, read port A0 up to A3 and write the value to port B4 to B7. So this part we are going to do it when the interrupt takes place. This part we are going to do it as part of the main function. So meaning when the interrupt happens, we skip and we come read A0 to A3, write the value on B4 to B7, and then we clear the interrupt flag. We return back here where we are implementing a 2-input exclusive OR logic gate. Right. Now, this question says we are going to use A0 and A1 as our inputs for the exclusive OR operation. And now, the very same A0 and A1, they are going to use, but this time around, from A0 to A3, we read the state of A0 to A3, and then we write the value to B4, from B4 to B7. We read A0 to A3, we write the value from B4 to B7. Right. Now, why are we writing to B4 to B7? I will say maybe specifically for this example, because we are going to use RB0 as an input. There's no way, even if we could, but it doesn't really make sense to read the whole of port A and write it as it is to port B, because B0 won't be an output, it will be an input. Right. So I want us to read A0, the lower nibble of port A, you read it, and then you write it to the higher nibble of port B. And then you are going to do that when you get RB0 interrupt on the rising edge. Right. But for normal operation, you will implement exclusive OR gate using RA0 and RA1 as inputs and port B2 as your output for that gate. Right. Let's now go draw the flowchart for this example. We do that by going to draw.io, and then we create a new blank flowchart, and then let's say we want to go to documents, and then under documents create a new folder, and then I'm going to call it interrupts. And then open that folder, save my file as flowchart under that interrupt folder. Now I've created now my window for the flowchart, starting with an oval shape. Start as always, starting with the main flowchart. Start, which is our origin 0, 0, and then we go to initialize. Initialize. Now, at initialize, we want to make A0 and A1 inputs, but not only A0 and A1, because the question further says read port A0 to A3. So A0 and A1 are inputs for the exclusive OR gate, but still here A0 to A3 are also inputs for the function which we're supposed to do in the interrupt. So we're going to set A0 to A1, A0 to A3 as inputs. That will have covered also that section there of A0 and A1. If we make A0 to A3 inputs, that will cover A0 and A1 also as inputs. So we want to make A0 up to A3 inputs, and now we have to also make RB0 an input, because it can only function as an interrupt if it is configured as an input. Right. And now the rest of the pins we're going to configure them as outputs, including RB2, RB4 to RB7. Right. Now we do that through our initialize stage, where we say at initialize we configure RA0 to RA3, initialize RA0 to RA3 as inputs, right? And because we have inputs on port A, we need to disable analogues, else they will affect the operation of those pins, because we want to use those pins as digital inputs. Disable analogues. Let me expand this table a little bit. And now configure RB0 as an input, the rest as outputs, right? And then, okay, all other pins are going to be outputs, both on port A and on port B. All of those other ones which are not used are going to be outputs, right? We also want to do something. Set RB0 interrupt on rising edge. Then after setting it up on rising edge, enable GIE and RB0 or the int E. Enable those bits, the GIE and the int E bits. Enable the RB0 interrupt. The easy way, I can even omit the GIE, because for me to enable RB0 interrupt, it means I must enable GIE and int E, right? So that's basically what we are supposed to do now on our initialize. Now you see there's a lot more work to do at initialize than just setting the IOs, right? We need to set up the interrupt rising on a rising edge, and then we need to enable our RB0 interrupt, right? After that, what is it that we're supposed to do? The main function says we need to implement a 2-input exclusive OR gate using A0 and A1 as our input. So we go into the main function. That's what it means. We go into the main function because it says here, according to the structure of using interrupts, after you initialize and you enable interrupts, you perform your main function. Our main function is to implement a 2-input exclusive OR logic gate, right? And now we will only leave this when an interrupt takes place, because we have enabled the RB0 interrupt at initialize. So now we need to implement our 2-input logic gate as it is stated here. 2-input exclusive OR logic using RA0 and RA1 as inputs and B2 as an output. We go and do that. So to implement that, we say now we are going to test. Remember now, for the exclusive OR, when any input is high, or when the two inputs are the same, the output is 0. When both inputs are zeros, the output is 0. When both inputs are ones, the output is 0. That's the exclusive OR operation. Right. Now we are going to do that by testing A0 here, and then we further go and test A1. Because those are our two. We're going to test A1 here, and then we also have to test A1 again. Right. So let me just move this table some. I'm trying to leave space for the other lookup table. Now, let's say here we are testing RA0. It can be either a 0 or a 1. If it's a 1, we come and test RA1. Still, if it's a 0, we come and test RA1. Right. So we're going to have that and that. And then here we say if we get a 0, and here this is if we get a 1. Right. Now what happens here? Let's start with the 0 side. When we get 0 and then we test this one and then we get a 0 again, where do we go? If we get a 0 again, we are going to come in we're gonna come here, and now this is if we get another 0. So when we get 0 and 0, what is supposed to be our output in terms of the exclusive OR? And then remember the output is on RB2. So our RB2 must be off, must be low, because the two inputs are both zeros. 0 exclusive or 0, you get a 0. Right. But what if RA0 was 0 but now RA1 is 1? What if RA0 is 0 but RA1 is 1? That will mean that our output becomes, I don't know what's going on. All right, if you have a 0 on A0 and then you end up with a 1 on A1, 0, 1 means our output will be high. RB2 will be high here. And now that will still be the case if, say, RA0 is 1 and then RA1 is 0. The output will still be 1. So I'm just going to go to the same block here. Come on. And then take this here. That will still take me to that block there, because we'll have 1, 0, 1, 0 for the exclusive OR, that's a 1. Right, that's a high. Now, if we get 1, 1, what do we do? If we get 1, 1, we have to clear the flag. We have to clear it. This is going to be the RB2. The output is going to be low again. Because 1, 1 is a 0, 0, 0 is a 0. And then the other two options, they yield an output of 1. I don't know what's going on, what's wrong with this, but let me this out. Perfect. Right, this is if we have a logic 1. 1, 1 for the exclusive OR, it's a 0. 0, 0 for exclusive OR, it's a 1. 0, 1, it's a 1. 1, 0, it's a 1. That's what we're supposed to do in the main function. And then we just connect those arrows in that particular fashion. And then the last thing for us to do is to say, let's go back to May. Let's go back to May. And this is where our main is going to be. That's our main program, right? This is where our main is going to be. Let me maximize that a little bit. Right? Now, these ones, they will just join in, going back to main. Going back to main. That's the flowchart for our main function. That's what we want to do for the main function. But now, remember we enabled an interrupt. Let's say at some point, while the PIC or the CPU is busy running and testing and writing, it doesn't matter where the interrupt takes place. When the interrupt might take place while the PIC is testing RB or RA1, or it might take place while it's trying. It might take place anywhere in the main function. It doesn't matter where. When the interrupt takes place, the PIC has to jump from wherever it is to what we call the interrupt service routine. The interrupt service routine starts also with an oval shape at address 04. Remember, the reset vector is address 00. The interrupt vector is address 04. So here we say ISR, interrupt service routine. Now, according to our problem statement, what did they say we should do? When RB0 interrupt occurs, read A0 to A3 and write the value to B4 to B7. So we are going to read port A and swap it around, swap the nibbles, and then write the value to port B, meaning taking the lower nibbles of port A to the higher side and then writing them to port B4 to B7 of the port B pins. Right. Let's go do that. When interrupt occurs, that will happen at 04. What is that we are supposed to do? We are supposed to perform the function, and then when we get an interrupt, address 04, that's our interrupt service routine, we need to perform the ISR function, the interrupt service routine function. And now in our case, the interrupt service routine function, it is reading A0 to A3 and writing to B4 and B7. That's what we want to go and do. So let's go and do that on our flowchart now. When we get to ISR, we want to read. So we want to read we are going to read here. Read port A. Actually, the instruction that we're going to use is read and swap port A. Swap means take the 4 lower bits, move them on the higher side, and take the higher 4 bits, take them on the lower side. because we want to take A0 to A3 to the higher side so that we can write them to B4 to B7, right? And we are only interested in A0 to A3. So A4, A5, A6, we are not interested in those. I'm going to mask them. I'm going to end this value with F0 to ensure that the rest of the other pins I'm not interested in, I force them to be 0. Basically, swap means I've already swapped those. Reading and swapping, it means I've already taken A0 to A3 to the higher neighbor. So I'm going to mask. Okay, mask by ending with 0x F0. It was going to be 0f if I didn't swap, because I'm reading A0 to A3. But I've swapped already that A0 to A3 to the higher neighbor. Hence, that becomes F0, not 0F. It's an already swapped version of A0 to A3, right? After masking, they said read port A and write it to port B. I need to write that value to port B. Then I will be done with the function that's supposed to happen in the interrupt service routine. Write the value on port B. Write the value on port B. Now I'm done with the function. But now that's not where it ends when it comes to interrupts, because we say before you return from interrupts, you need to clear the interrupt flag. Although we are done with the function, we still need to clear the flag before we return from interrupts. So I need to go and clear the interrupt flag. So what do I do is I add another block that says now there clear RB0 interrupt flag. Clear RB0 interrupt flag, clear that indication that the interrupt took place, and then the last thing to do is to return from interrupt. Return from interrupt. Return from interrupt. That will be our interrupt service routine flowchart. So for this application, we now have two flowcharts instead of a single flowchart. And then this one, it is very easy. It's just arrows facing all the way down. And now, remember, when you get an interrupt, we jumped there and then we performed all of this. When we return, we jump back into the main program, continue where we left. So these are the two flowcharts that are going to help us write a program for this function. So now we have created the flowchart. Let's go write the program as the example instructs us to. It says there, draw the flowchart and write an assembly program to do the following, where we need to read two inputs, A0 and A1, implement the exclusive OR logic, and send the output on RB2. That is part of our main function. And when we get RB0 interrupt, we need to read the whole of port A0 to A3 pins. Those 4 bits, lower 4 bits, we need to read them and write them to the 4 higher bits of the port B, being B4 to B7. Let's go create a project and then write an assembly program to do just that. Always, when you write a program that has to do with interrupts, you'll always start with the main program. There's no way you can start with writing an interrupt program, because the interrupt program is part of the main one. It's just that you leave the main function to execute the interrupt and then comes back to the main function, and the interrupts you enable them in the main function. At initialize, that's where you enable interrupts, right? So project wizard, next, I'm still using the 16F818, so I'm not going to change it. If you're using a different PIC, you can scroll down or type the PIC you're using. Next, we are using assembly language, so the tool suite is MPASM assembler. Next, now I need to browse and create a project. Now I'm going to create a project and save it under documents, and now give it a folder that says, oh, I don't even have to give it a folder. We had a folder where we saved the interrupts. So I'm going to go into interrupts. This is the folder where we saved our flowchart. So I'm going to go into that very same folder and give this project name interrupt as well. Interrupts, right? And then click save. That's the location of my project under documents interrupts. The file name is interrupt. Click next, nothing to add. Next, summary of your project, finish. Now I have my project created. I need to add a source file to the project. New file, save that new file as. I need to go to interrupts. So this is interrupts. I can give it the same name, interrupts.asm. Tick that box that says add file to project, save the file, and then we can start writing our program, right? As always, I'm going to start by writing the basic instructions required to implement an assembly program. List P equals to 16F818, and then we have include hashtag include P 16F818.inc. Include this file, which actually this file has in it definitions of all the special function registers for us, so that we don't have to equate or state those names and their relevant file addresses. That has already been done for us in the file. We just make use of that file in this project or in this program by including the file in the program, right? So the first instruction, we are informing the compiler that we are using the PIC 16F818. The second one, we are making use of that P16F818.inc file, so that we can use the names of the special function registers without having to declare them first, because they're already declared for us in that file. And now, as always, your program has to end with end, and then this states the end of our program, the end of the program, right? This is for a compiler to say, now we have reached the end of our program. Build that, select absolute option. That should build successfully. Now we can start writing our program. We start writing our program with the origin 00, meaning we are now firstly implementing this flowchart here. We're implementing this one. Before we can implement the interrupt, we need to implement the main one. We start at origin 00, right? So we say org ox00, which is our reset vector, and then we say go to initialize. So initialize is our label. So we say go to initialize, and then at initialize we need to set up our IO pins. How are we supposed to set up those IO pins? We look at the flowchart. It says that RA0 up to RA3 must be inputs. To access those, we need to be in bank 1 so that we can access the trace registers. Bit set file status comma RP0. This means we are going into bank 1. And now we want RA0 to RA3 to be inputs. Those are 4 lower bits. And then if we make all those 4 lower bits once, the hexadecimal becomes F. So we say move 0x, the 4 upper bits are 0, the 4 lower bits is F. So we move F into W, we move W into trace A, right? Now that will make our RA0 to RA3 inputs, right? Now we want to make B0 an input. Our initialize, we want to make B0 an input. It says here RB0 must be input there. RB0 must be input, and then the rest of the pins on port B can be output. So we are going to do that. Move literal to W. To make only B0 an input, we move 0, 1 into trace B. Move literal to W OX 0, 1. Move W to file trace B. But if you want to follow the flowchart line by line, it is still fine. After making port A pins inputs, we can start by disabling analogues before we make B0 an input. We can start by disabling analogues. So after making RA0 to RA3 inputs, let's start by disabling analogues. So we are following that table or that rectangle, the information in here. We are following it line by line. It's not a must that you follow it line by line. You can disable analogues even after you have enabled interrupts, as long as in the end you have done all that is in here. But if you want us to follow it line by line, we will make RA0 to RA3 inputs, then disable analogues, then make RB0 an input. So we made RA0 to RA3 inputs. Here we want to disable analogues. Move a literal value into W OX06. Move W to file AD-con1. This basically disables analogues, right? Now, and then this one makes port B0 an input, the rest as outputs, right? Now, the next thing to do according to that, okay, the rest of the other pins as outputs, we need to set RB0 interrupt on rising edge. We need to set RB0 interrupt on rising edge. How do we do that? Looking at the option register, bit 6 of the option register. To do rising edge, we need to set bit 6 of the option register. And now, another question is now, where is option register? In which bank do we find option register? There it is. Option register is in bank 1. So while we're in bank 1, we can set bit 5 of this option register. So option register, basically you get it in bank 1 and in bank 3. But because we're already in bank 1, we're going to do this while we're in bank 1. So we're going to go back to our program and say, while you are in bank 1, let's bit set file. Bit set file we want to set only bit 6 of the option register. So the register is option. Be aware how that option register is written. It's option underscore register, and then we want to set bit 6, or we can use the name of that bit if necessary. Let's look at that option register, how it is referred to. That will be here. The option register, it's option underscore reg. They didn't specify how. You see, all of these other register, they give it a name semicolon and they describe it. But option register, they didn't do. But fortunately for you, I know how it is referred to. So it is referred as option underscore reg, and then the bit we want to set is bit 6. So instead of writing that bit 6, we can just use the name of the bit. But you need to know now, what will that name be, or what is the name of bit 6 of the option register? The name of bit 6, here it is. External RB0 interrupt edge select. So I'm copying that name. I can use that name here instead of comma 6. I can say comma that name. That will still do the same job. Now, according to my flowchart, I am now done. Okay, not yet. I just set the RB0 interrupt on rising edge there. I need to enable the interrupts. Now, to enable our interrupts, looking at the intcon register, to enable our interrupt, I need to first enable the external interrupt there, and then enable the GIE. And then that's when I went to the intcon and said, GIE is going to be 1. We're not going to use peripheral, this is going to be 0. We are not using timer 0, since this one's going to be 0. We are using the RB0 interrupt. This has to be 1. So that value is 9, right? And now we are not using RB0 port B on change, bit 3. We are not using port B on change, that's 0. And now the flags are the indicators. I said the flags on default, we initialize them as zeros. So the value that we must move into incon to enable our interrupts, it is 9, 0, enabling both the global interrupt and the port B, the RB0 external interrupt. Setting the global interrupt and the external RB0 enabled interrupt will actually enable our interrupts. So that's what we need to do. We go back into our code and say, well, where do you find incon? In which bank do you find incon? We go back to our program memory, our memory organization, and we look at incon. You see, incon is found in all the banks. Incon is found in all the banks. We have incon in bank 0, bank 1, bank 2, and bank 3. So there's no need for us to do it in a specific bank because it is found in all the banks. So we can just go back to bank 0, bitclear file, status RP0. Now here we are switching to bank 0, and here we were enabling the rising edge. So RB0 interrupt on rising edge. We go to bank 0. We can still access the intcon in bank 0. So what do we do? Move a literal value into W. The value is 90, which we got from for the intcon, and then we move that into intcon. Move W to file, intcon register. By doing that, we are enabling, we're actually enable RB0 interrupt. Right, we are enabling the RB0 interrupt there. And then after enabling the RB0 interrupt, The next thing that we need to do is to, according to our flowchart, we now need to test our pins. We need now to test our pins and then write to bit 2 depending on whether our logic was 1 1 or 1 0 or 0 0 or 0 1. So we are going to test. I want to start by testing RA0, and then that's going to be our main function. So that's where our main is going to start. So we start by saying at main, let me just put a space by enter there. At main, we start by testing bit test file, skip if set. We can use skip if clear if you want. Port A RA0. I'm testing RA0. If it is set, I'm going to skip. But if it is not set, I'm going to go to a label, right? So if it is not set, go to test A RA1. If it is not set, I'm going to go to test RA1. But if it is set, I'm going to skip. Now, if it is set, what is it that I want to do if it is set? If it is set, I want to come and test RA1. If it is set, I'm directly coming here. But if it is not set, I'm going to come to test RA1 on the other side. But if it is set, I'm directly coming here. So say skip if set, I jump directly to testing now. Bit test file, skip if set again. Port A RA1 this time around. If RA1 is set, I'm going to skip. Then it means I have set and set. I have 1 1. But if I have 1 and then the other one is 0, what's supposed to happen according to the table? If I have this as set, I skipped and I came here and I test this, it's not set. I have to go set RB2. I have to go to set RB2, right? Now, if I go to set RB2, I need to implement it in my program. Go to set RB2, because RB2 is the output for my exclusive OR logic, which I'm supposed to implement, right? Now, if A0 was set, I skip, and A1 is set, I skip. It means they are both 1. A0 and A1 are 1. If I have 1 and 1, what's supposed to happen? I clear B2. So bit clear file, port B, RB2, and then after clearing port B2, what do? Go back to main. And then I have go to main, right? Now it means I am done with this section. Skip if set, load this, and then go back to main. Now I still have to define what set A2 is. I still have to define what test RA1 is. Let me start with testing RA1. If I go back to testing RA1, or maybe I should start by finishing off set A2. Set A2, at set A2, it means now what happened before I got to set A2? I said test RA0. RA0 is 1, I skipped, and I test RA1. RA1 is not 1, so I don't skip. There's a label there. Go to set A2. So I had 1 0. According to my flowchart, if I have 1 0, what must happen? I must go set B2. So at set B2, I'm going to say bit set file, port BRB2, and then after setting that port B, what do? Go back to main. So I have go to main, right? Now that will conclude this section of the program. I'm now left with having to come and test here. That is the test label that I need to go to. This is the test label that I need to go to. I'm testing RA0, and then if RA0 is not set, it means it is clear. I'm not going to skip. It's going to jump to test RA1 and at test RA1. So I'm testing this, skip if set, but if it's not set, I have to come and test. So at test RA1, I'm going to test A1 there. Bit test file, skip if set, port A RA1. Now, if it is set, so I had a 0. When I test it and it is set, I'm going to have to come here. And then this label is actually the same as set RB2, which I had there. Right. So if it is set, I'm going to come here. But if it is not set, then I have to go to clear B2. I have to go to clear B2. So if it is not set, I'm going to say go to clear RB2. But now, let's look at it. Here, I'm clearing RB2. And here, I'm clearing RB2. Instead of doing it 2 times, I can take this to that section. Because they're actually doing the same thing. So in my program, I already have a place where I clear B2. I just have to specify where is it. So I'm going to copy that label. This is where I'm saying bit clear file port B2, so I can put this label here, clear B2. Right? So it's going to jump here, clear B2. After clearing B2, what does it do? It goes to main. Still going to do the same thing. After clearing B2, it's gonna go to main. And now when it is set, so if I had a 0 and I have a 1, I have to go set B2. There's a point where I set B2, and then the label was bit set file port B2. So here I'm going to say go to set RB2, and then that will conclude my main function. That will conclude my main function. If I build this, it should build successfully, right? But that program is not complete because I have enabled interrupts. If an interrupt takes place, the program should be able to jump to what we call the interrupt service routine, right? And now the interrupt service routine is address program address 04. So we need to initialize it here as well. Origin OX04. This is our interrupt vector. It means now, while your PIC is busy executing the main function, while it is busy executing the main function, if an interrupt takes place, it's going to leave whatever it's doing. It doesn't matter where the interrupt, where the program is when an interrupt takes place. When an interrupt takes place, this PIC is going to jump to origin 04. And then just under that origin 04, that's what we need to write for the interrupt service routine. So we can say go to here, interrupt service routine. And our interrupt service routine, you can put it wherever you want. I'm going to put it just under interrupt service routine. You can put it at the bottom there, just before end if you want. You can put it at the bottom there, just before end. It will still work, but I'm going to put it there. My go to add interrupt vector, go and perform the interrupt service routine. That's basically what this flowchart is saying. At origin 04, let's perform the function which we need to do for the interrupt service routine, and then we clear the interrupt flag, and then we return from interrupt. To see it clearly, this is what it means. It says here, at origin 04, go and perform the ISR function, clear the flag, and then return from the ISR. That's what we want to do. But in our case, the ISR function has been broken down for us to be able to do it step by step. We want to read port A 0 to A3, swap it around, mask it, and then write it to port B4 to B7, clear the flag, return from interrupt. So we start by reading and swapping port A. So at ISR, at the interrupt service routine, we are going to start by swapping file. Read and swap that file. That file is port A. Save the swapped result into W. Right. Now we want to mask it. End literal with W, the swapped version with F0, and now we want to write it to port B. Move W to file, port B. It means now what we have done is reading and swapping our port A, masking it with F0, and writing the value on port B. What is that we need to do next? We need to clear the RB0 interrupt flag. Very important. We need to clear this flag. How do we do it? We actually need to access the intcon register. Now that flag is available on the intcon register. This RB0 interrupt flag. This is the flag. You see, it says this is when the interrupt occurs, this bit will be made 1 to show that the external interrupt has occurred. And then in bracket says we must clear this in software because it is set automatically in hardware. When the interrupt takes place, we must clear it in software before we return from interrupt. This is the flag for the RB0 interrupt. We don't clear the flag for timer. We are not using timer 0 interrupt. We are not using port B0 interrupt. We are using the RB0 external interrupt. We need to clear the flag for that interrupt before we return, because that's the interrupt we enabled, right? Meaning the moment we go to the interrupt, we know for sure that was the cause of the interrupt. So we need to go and clear this interrupt flag. It is bit 1 of the intcon register and the name is intf. So I'll just basically say bit clear file intcon, intf. That is how we are going to clear that flag. So by saying bit clear file intcon, intf, we are clearing the interrupt flag. Clear RB0 interrupt flag, right? And now what is left of us according to our flow chart is to return from interrupt. After clearing the flag, we need to return from the interrupt. How do we return from the interrupt? By making use of an instruction. It is a return instruction, but this is a specific return. You return from interrupt. Int FIE. Okay, return from interrupt with enable there. I will explain maybe on the next video what exactly that does that mean, or what happens actually on this video later on. I will explain that to you. But now we are saying return from interrupt with enable by enabling the global interrupt there. And this one, it is where we are writing to port B the value which we read and swapped from port A. So read and swap port A nibbles. Here we are masking, mask, write to port B, return from interrupt. Clear the interrupt flag, then return from interrupt. So this instruction here is just return from interrupts. So to return from interrupts, you don't use any return. You use specifically this instruction that says return from interrupt. I will explain what is the significance of this instruction. Return from interrupt. So that concludes both our flowcharts, but they are the program is still one ASM file. Although it is two flowcharts, we are still having one ASM file. Right? This is still one program. One program. Making use of interrupts, we have to have two flowcharts, but the program is still a single program. So let's build this and then see how it's going to run on the simulator. We're no longer going to use 7 segments. Let's firstly look at the circuit first. How the circuit will look like. So for that, let's look at this. I'm using PIC 16F818. A0 up to A3 are inputs. We have switches there connected. And then A0 and A1 are inputs for the exclusive OR gate. And the output of that exclusive OR gate is A2. See, that's the LED for the exclusive OR gate. So the exclusive OR gate is going to consider A0 and A1. But now, on port B4 to B7, we have 4 LEDs there. We're going to read all port A pins A0 up to A3, and the state of these pins, we are going to write them on B4 to B7. Hence, we have 4 LEDs connected to B4 and B7. Your VDD connected, your VSS connected, your M clear pulled high through a pull-up resistor there. Right. So this is basically the typical circuit using the internal oscillator. We don't need an external circuitry for the oscillator there. So let's simulate this program. I'm going to load now under documents, interrupts, our file, and say start. For exclusive OR, you see now B0 is an input, A0 up to A4, A0 up to A3. This is A0, A1, A2, A3. Those are inputs. Remember, A5 can only be an input. It cannot be used as an output. So it doesn't really matter what we do with A5. And this A5 is actually our M clear, because we're not using it as a digital I/O. We're using it as M clear. It's connected to logic 1. Now, what you need to be aware of now is with 2 input zeros, our B2 is also 0, because that's an exclusive OR gate. If I do this, if any of the inputs becomes 1, B2 becomes 1. So this one, if that one becomes 1, B2 becomes 1. If they both become 1, B2 is 0. I'm changing these pins, but only the exclusive OR part is working. The reading of port A and writing to port B is not happening yet, because it only happens when there's an interrupt. It is waiting for me to interrupt that, to change this logic from low to high. That's when an interrupt is going to happen, meaning that's when it's going to read. So let me make them 1, 1. B0 and B1 are 1. When I generate an interrupt, you see, it reads now that A0 to A3, it reads it and then it writes it to B4 to B7. So that is A0, A1, A2, A3. A2 and A3 are off, A0 and A1 are set. If I change that, it's not going to automatically change. It's only going to change when I generate an interrupt again. Rising edge, it's only then it changes. The falling edge doesn't generate interrupt. Remember, we set our interrupt on a rising edge, meaning when it changes from logic 0 to 1. When it changes from logic 1 to 0, it's not going to generate an interrupt for this application, because our interrupt is on a rising edge. Right. So if I make them all ones, you see, my exclusive OR, it is still working there regardless, because exclusive OR is making use of those 2 inputs. If I make all of them once, I need to generate an interrupt for that output on port B to be updated. Generate an interrupt. You will read all of those. They are all on all port B4 to B7 are on, right? So basically, that's what interrupts are, and that's how we make use of interrupts in the PIC microcontroller, right? Now, I said I wanted to explain what happens here with this instruction. Basically, it has to do with what happens when we go into interrupts. Let's go back to our main flowchart for the interrupts and then discuss a few things. For interrupts to take place, we need to first enable interrupts and also enable the GIE. Enable the GIE, right? So GIE enables all the interrupts. For any interrupt to take place, GIE must be set. Let's assume that we are using more than one interrupt. If I was using both RB0 interrupt and the port B on change interrupt, if I was using port B on change interrupt and the RB0 interrupt, say for an example, the RB0 interrupt takes place first, it means I'm going to jump into interrupt, and then while I'm in interrupt into the interrupt service routine, I cannot jump to interrupt while I'm in an interrupt. To prevent jumping to the interrupt, let's say for example, the RB0 interrupt took place, I jumped to the interrupt, and then the port B on change also takes place because I enabled both of them. If this is still enabled, the program is going to try to jump to the interrupt while it's already in the interrupt. So what happens when any of the interrupt takes place, whichever one takes place, the first one that takes place, when the PIC jumps to the interrupt service routine, it clears the GIE. It automatically internally makes GIE 0, ensuring that no other interrupt will take place, because if it makes this bit 0, no other interrupt will take place because we are already in the interrupt. We are going to service the interrupt and clear the interrupt flag. After you clear the interrupt flag, when you execute return from interrupt, that instruction, return from interrupt, basically it says return from interrupt also enable that GIE. It returns from interrupt, and in the end it re-enables that GIE because that GIE was disabled by the CPU when you went to the interrupt, to prevent going to the interrupt while you are already in the interrupt, right? So when you return from interrupt, you have to return by re-enabling that GIE because it was disabled internally. If you use a normal return, you will still return from interrupt, but the problem is you will return without setting GIE. It means now after that return, no more interrupts will take place because GIE won't be enabled. No more interrupts will take place because that GIE will be off, because every time you go into interrupt, the CPU internally disables GIE to prevent what we call recurring interrupts. Interrupt happening while you're in the interrupts, right? So when CPU disables that GIE when it goes to the interrupt, before you return or when you return from interrupt, you need to set that GIE. And now the return from interrupt instruction does that for us. Hence, we have to use the return from interrupt, not just any other return. That's the purpose of that return function or return instruction. Now, guys, I hope this makes sense in terms of interrupts, and then hopefully on other tutorials we will look at having more than one interrupt and how we work with more than one interrupts, and how can we differentiate which interrupt took place. We basically do that by monitoring the interrupt flag, but I will have to do it practically to show you how that is done. I will do that at a later stage. For now, just make sure that you understand the concept of interrupts and you can make use of interrupts in your applications. Okay, thank you guys. I'll see you again on the next video tutorial. Enjoy.